Yeah, thank you, Thierry, and thanks to the organizers for the invitation. So I'm going to be talking about the rotational motion of anisotropic particles that are sedimenting through a stratified fluid medium. Okay? And as you'll see, the anisotropic particles are really spheroids or ellipsoids of revolution. And so this part of the work that deals with anisotropic particles is being done by my student, Arun Kumar Varanasi, who's poised to graduate, and my collaborator, Dr. Navneet at IIT Roper. And I'm hoping if I have time towards the end, I'll also speak about some work on the flow field around spherical particles, the flow field at large distances, again, moving in a stratified ambient. And that's work done in collaboration with Anubhab at IIT Madras, who's one of the organizers, and his PhD student, Ramana. So the general motivation for this can be very short. You know, the atmosphere and oceans are both stably stratified. So if you have stuff moving either in air or in water, then there will be situations where you will encounter particle motion in a stratified setting. And if the time scales and length scales are appropriate, then the stratification will have an effect. And so the stuff that is moving can be passive particles, and I've just put in images of examples of passive particles. This is marine snow. That's the term used for dead, decaying organic matter or inorganic matter. And then you have synthetic passive stuff, which is microplastics. And the idea of these images is to show that the shapes usually in nature, I mean, almost always in nature, are very far from the idealized spherical geometry. And then you have active particles, which are really the microscopic swimmers. And these pictures at the bottom, this plate of about 9 pictures shows various zooplankton, which are really the smallest marine animals feeding on the marine algae, which are the phytoplankton. Okay, so that's again to show you that they can be very small. So the smallest of them are about tens of microns. Okay, with the largest krill being about a few millimeters in size. Okay, but they again depart very much from the spherical geometry. And here is another plot of the phytoplankton sample plotted against aspect ratio. So that dashed line there, the vertical dashed line here, denotes the spherical shape, which is the aspect ratio of unity. And you can see that the distribution peaks at an aspect ratio of about 5. So even algae or swimming phytoplankton peak at a shape, the most frequently encountered shape is very far from a sphere. Okay, so that's sufficient motivation for us to worry about anisotropic particles. And an interesting motivation is actually in the context of active particles. About a decade or so back, in 2009, there was the provocative proposal of a biogenic source for ocean mixing. This was proposed by John Daviri in a Nature article that was quite controversial. And the idea was, as I said, controversial because one normally imagines the ocean, the energy input for the ocean mixing to come from large scale sources, like the winds. We had an example, winds driving a boundary layer in the ocean, the surface layer, and the instabilities and so on. And then tidal mixing. We've seen several examples of tidal mixing / instabilities in this conference in earlier talks. But the proposal of the biogenic mixing was at the other end of the spectrum. The proposal was that there are a large number of these small swimmers in the oceans. So if you actually worry about the aquatic biomass, the maximum fraction of the aquatic biomass is at the smallest size scales. Okay, so the idea therefore was that the large number of very small size swimmers will input enough energy that will somehow find its way to larger scales as available potential energy and then be converted by other mechanisms into mixing oceans and internal energy and so on. Okay? So I had at that time, I was asked to review that article, and I found that proposal, it was based on a single swimmer and didn't account for stratification. Okay, so it seemed a little far-fetched that a single swimmer could provoke a large-scale mechanism, single swimmers acting independently because of their small sizes. Okay. But the question remained, the interesting question remained as to, if we do consider a single passive particle or an active particle, that is a microscopic swimmer, how much volume is really displaced by this particle. And this displaced volume is known as the drift volume. And I'm talking about the drift volume because that was the basis of the original argument in this paper, in that, if the Reynolds number is low, then you can actually show that the drift volume is larger. Okay? And if you ask the question for a homogeneous particles, a homogeneous ambient, so in other words, you ask for a particle moving in a constant density fluid, as to how much fluid can it drag, what volume of fluid is the particle able to drag in the limit of long times, okay, then the answer is infinite. Okay? And that's because in the sketch here, you see that there is a trailing viscous wake, and the velocity in the wake decays very slowly. It just decays as the reciprocal of the downstream distance. And that decay is slow enough for it over long times to drag an infinite amount of volume. Okay? So the answer, rather surprisingly, perhaps, turns out to be infinite in the homogeneous ambient, which lends some sort of credence to the drift volume hypothesis that if it were indeed a homogeneous ambient, then yes, a single particle might be able to drag a significant amount of fluid. Okay? But the authors had also neglected stratification, and that became an interesting question. Okay? So how much volume will a particle drag, a passive or an active particle? And I'm worried more about a passive particle because their velocity field tends to be stronger. How much volume does a passive translating particle drag in course of its motion through a stratified ambient? And unlike the homogeneous ambient, we expect this to be finite because the intuitive notion is that at sufficiently large length scales, you simply can't push fluid vertically. The potential energy penalty is too much, and therefore the nearly vertical motion in the vicinity of the particle will transform to horizontal motion. Okay? So this, in fact, was the original motivation for my starting to worry about stratified fluids. So I thought I'll mention this. I'll try and return to it briefly at the end of the talk if I have time. Okay. But there is a more specific motivation for this talk, and that is anisotropic particles. So the specific motivation is a pair of experiments, quite recent, less than 2 years old. So this is the left-hand side experiments with disks settling in a linearly stratified fluid. So these are experiments that are among the first to systematically explore the motion of anisotropic particles in a stratified ambient. Okay. So as I said, Matthew Mercier had his experiments in a linearly stratified fluid. So that linear stratification is indicated by this figure on the left, where the solid line indicates the linearly varying density gradient. And that leads to a constant buoyancy frequency here. Okay? And the authors experimented with sedimenting disks, okay, one of which is shown here. And the interesting thing was, as you can see here, the disk was released from rest at the top of the container, a cylindrical vessel, and it settled for a while in the horizontal orientation. Okay? Now, as it settles, its velocity decreases because there is a critical level near the bottom of the tank where the density of the fluid has increased enough to be equal to the density of the disk. The density difference between the disk and fluid is fairly modest. And so as the velocity decreases, as the disk slows down, there comes a point at which the broadside settling orientation here appears to become unstable. The disk rotates and rotates almost to an edgewise configuration as it settles further, continuously slowing down. And then in the end, in the final phase, it's reached the neutral buoyancy level, and then it starts to again turn back and adopts eventually a horizontal orientation. Okay, so this was very interesting, particularly because if the fluid were not stratified, if it were a homogeneous ambient, then it's quite well known that if you have an anisotropic particle, then it tends to settle in a broadside on configuration. Okay? So starting from any orientation, it rotates towards the broadside on configuration. And this is true for Reynolds number up until about 100. So it's certainly true for the small Reynolds numbers that I'm going to be talking about. Okay. Above a critical Reynolds number, there emerges a path instability, wake mediation, and so on. But the experiments here were carried out at Reynolds numbers well below that bifurcation threshold. Now, the second set of experiments were by Mrkowska, and this involved a different sort of stratification. It sort of mimicked the oceanic structure. So you have the analog of the surface layer above, and a strongly stratified pycnocline in between, and the deep ocean analog below. Okay, although because it's the lab analog, the Brunn-Weissela frequency is much higher than the oceans. Okay, but nevertheless, you have a stratified layer sandwiched between two homogeneous layers. And importantly, in this case, there was no neutral buoyancy level. So the particles were heavier than the largest density corresponding to the bottom layer. And the experiments were again using disc-shaped particles. And you can see two of the particle settling trajectories. Okay? And the disk had many aspect ratios. And the authors just demarcated 10 as a threshold so that disks with aspect ratio less than 1/10 would be thin disks. Okay, so the aspect ratio that I'm going to be talking about is the inverse of these numbers. And if it's thicker than an aspect ratio of 1/10, then it's termed the thick disk. And you can see that the thin disks sort of exhibits a pattern similar to that was observed in the experiments on the left, in that there is a transition from broadside on to edgewise settling. Okay, so again, there's the indication of stratification tending to rotate the particle in the reverse direction. Okay, and then once it exits the stratified zone, it goes back to the broadside on orientation. And the thick disk seems to not go the complete way, but instead it stays at an intermediate orientation before finally reaching the bottom layer and then reverting to a broadside on configuration. Okay, so my main motivation will be to explain these observations. Okay, now these experiments were done at Reynolds numbers of order unity. So they were not large, but they were not small either. Okay, the Froude numbers were also of order unity or a little smaller. Okay, but as we'll see, the theory is going to be at small Reynolds numbers, and the argument is that we can explain most of these features, practically all of them, using a small Reynolds number theory. And it turns out that there is a new dimensionless parameter that comes about that will be the viscous Richardson number. So I'll introduce it as we go along. And so this is to just tell you the governing equations that matter. So you have the continuity equation, the equations of motion, and the convection diffusion equation. So I'm just showing this because they've been written in dimensional form. But by virtue of the equations of motion, I know I'm going to have the Reynolds number as a parameter. Okay? And because I have the convection diffusion equation, I'm going to have the Peclet number as a parameter. Okay? And so the Peclet number can be small or large. In the experiments, it was very large because salt was used as the stratifying agent. And we know that the Prandtl or Schmidt number for salt is around 700. And so I'm going to start from the baseline scenario, which is just consider no stratification, so a homogeneous ambient, and no inertia. So Reynolds number is 0. So I'll end up with the Stokes equations here with the continuity equation. Okay. And it's quite well known. The Stokes equations are like the Laplacian. So a translating particle is like a momentum source. And therefore you have a velocity field that is like the Green's function of the Laplacian in 3D. So it decays like 1/r, UA/r to be specific. Now, the problem with the Stokes equations are they are what is termed not a uniformly valid approximation. And by that, what I mean is that if you worry about an unbounded fluid domain, then, and that's the case that you'll be worrying about, an anisotropic particle moving through an unbounded fluid domain, okay, then there is always, regardless of how small Reynolds number is, okay, or how weak the stratification is in this case, in our experiments, there is always a distance large enough beyond which the viscous forces become subdominant to any weak perturbing influences. In our case, those of inertia and stratification. Okay, so there is, loosely speaking, a boundary layer at infinity where you have to give up the Stokes approximation and account for the other weak forces at leading order. Okay? Now, this was recognized by Oseen more than a century back. And so in our case, Oseen's recognition was of inertia becoming a dominant influence at larger distances. Okay? And in our case, we'll have to worry about stratification. Now, I'll just, so the key ingredient here is to be able to estimate that length scale, the critical length scale beyond which inertia becomes comparable to viscous forces, or stratification becomes comparable to viscous forces. So for each new physical effect, there exists a new length scale that governs the dominant balance at large distances. Okay? So if we go along the lines of Oseen, the familiar case, I'll try to go through the scaling analysis for inertia. So the idea is the following. So you can estimate the length scale on a self-consistent basis in that you use the Stokes solution as the starting point. So if I take the Stokes solution, which is UA by R, A being the size of the sphere or the particle, then the viscous forces, which are mu del squared U, turn out to be mu UA by R cubed. So that's just 2 more R's in the denominator because of the double derivative here. And the inertial forces at large distances is primarily the convection of the disturbance field by the ambient flow in a reference frame that moves with the particle. And so they turn out to be, actually I missed an R here in the denominator. It should be rho U squared A by R squared, okay, because U is 1 by R, grad U is 1 by R squared. So the key thing is that the inertial forces decay at a slower rate than the viscous forces. So there comes a length scale where they become as large as the viscous forces, regardless of how small the Reynolds number is. And this screening length, so-called inertial screening length, is nu by u, the ratio of the kinematic viscosity to the velocity of translation of the particle. Okay, so if I write it in units of the particle size, it is A Reynolds inverse. So it has the intuitive property that as Reynolds decreases to 0, that screening length recedes to infinity. Okay, so at length scales of order, the inertial screening length or larger, I can no longer use the Stokes equations. I have to use inertia at leading order, okay, which are known as the Oseen equations. Okay. Now, with stratification, like I said, you have the option of choosing the Peclet number. Okay. Now, if it's salt, then unless your particle is very, very small, the Peclet number is larger than unity. Okay, so for larger than a few microns, Peclet is in excess of 100. And so if we talk about the large Peclet limit, okay, then now we have a heterogeneous ambient, remember, so we have a stably stratified ambient, okay? And the particle, as it moves through it, that Stokes disturbance field convects the density field, creating a density perturbation. So you got to first estimate the density perturbation, which will give you an estimate of the buoyancy force, and then you equate the buoyancy and viscous forces to find your screening length. So the idea is that the screening length in this case is determined from a balance of buoyancy and viscous forces. And for large Peclet, it's particularly easy because the density perturbation is just generated by the convection of the baseline stratification by the disturbance velocity field. So in other words, the density is conserved as the fluid element moves from one point to the other. So when that fluid element conserves its density and moves to another point, the density perturbation there is just the amount by which the baseline density has changed minus the original density. Okay? And that is just the baseline density times the distance through which the fluid element has moved under the influence of the disturbance velocity field. The disturbance velocity field we know is UA by R, dt is dr by u, r being the distance. So when you do this, because the velocity field decays only like 1 by r, you get that rho prime is actually independent of r. It is UA times the density gradient that characterizes the stable stratification. So now you have rho prime, you multiply it by g to get the buoyancy force per unit volume, which is A grad rho infinity times g, okay? Sorry, this u should not be there, the u's cancel out here. And now you equate this buoyancy force to the viscous force. The viscous force was already estimated in the inertial screening length argument. If you do that, then you get an estimate for the stratification screening length. And you can see that it comes out to be the cube root of the kinematic viscosity times the velocity of translation by the square of the buoyancy frequency. Okay, so you can write grad rho infinity here in terms of the Brunn-Weitzeler frequency. And so if you, so this is where you get a new dimensionless parameter. So if I again try to write the stratification screening length in units of A, then I get a new dimensionless parameter under the cube root, which I call the viscous Richardson number. Okay? So it's the viscous Richardson number that really governs the relative importance of viscous and stratification forces. And the screening length is in units of the particle size is the inverse cube root of the viscous Richardson number. Okay, so to give you an idea, if we go back to the oceanic ambient and consider a sub-millimeter swimmer, then the viscous Richardson number turns out to be about 10 power minus 8. Okay, that seems very small, but we are also talking about the cube root. So it's not really small, it's 10 to 100 times the particle size. So this is the definition of the viscous Richardson number. And if I were to relate it to the usual measure of stratification that's been discussed a number of times in earlier talks, which is the Froude number, then the viscous Richardson number is the Reynolds by Froude squared. Okay? So whatever I'm going to be talking about here has to do with small viscous Richardson number, okay, where stratification forces come into play at large distances from the particle, okay, from the anisotropic translating particle, but exert a singular influence in that the flow field looks very different beyond that length scale, which is the stratification screening length. So I've just highlighted the 3 screening lengths. Now, what I didn't tell you was the screening length for small Peclet. Okay. Now, you need not actually go through this elaborate argument, though it tells you the physics. But a simple way of arriving at the screening length is to say that, you know, it governs the physics at large distances from the particle. So the size of the particle no longer matters. Okay, and therefore the question is, can we combine the other physical parameters in a way to generate a length scale without the particle size being involved? And as you can see that nu by u, the inertial screening length, is indeed independent of A. So is the stratification screening length at large Peclet. And if you come up with a similar arguments for small Peclet, this turns out to be the small Peclet screening length. Okay, stratification screening. So this is the summary. Okay, the inertial screening length in the classical case, which was first implicitly recognized by OC, is ARE inverse. The large Peclet stratification screening length is A times inverse cube root of the viscous Richardson number. And the small Peclet stratification screening length involves both the viscous Richardson number and Peclet. Okay. So the picture is the following. So I'm going to be talking about first the small Peclet problem, okay, before going to the large Peclet that, remember, has a more direct connection with experiments, because the Peclet was certainly large in the experiments that I spoke about. Okay, so the intuitive picture is this way: you have a particle, and the particle size is A here. Okay, I've denoted it as a sphere, but in the actual problem, it will be an anisotropic particle. So you can, the dashed circle here has a radius of order the relevant screening length. Okay, so for small Peclet, the screening length is what we just wrote down in terms of the viscous Richardson and Peclet. So beyond this, at distances of order, the dashed circle and beyond, stratification forces become comparable to viscous forces. But on length scales of order A, viscous forces are dominant. Okay? So another way of saying it is, you can use Stokes approximation as a valid approximation in this inner region where the distances are of order A, but you have to use a more complicated leading order equation if you go to length scales beyond the dashed circle. Now, the same situation is for the large Peclet, except that the outer circle now has a radius of order the inverse cube root of the Richardson number. So here I've again written the definition of the viscous Richardson number. So in what I'm going to be talking about, remember, there is also a second screening length, which is RE inverse, that we derived on the earlier slide. So in each of these cases, whether it be small Peclet or large Peclet, there is in principle an inertial screening length, a second sphere, whose radius scales as the inverse of the Reynolds number. But we are going to assume that Reynolds is small enough for that inertial screening length to be so large as to be irrelevant. Okay, so what we are going to be talking about is exclusively a consequence of stratification and viscosity, with inertia not coming into play. And this makes sense again in light of the experiments, because remember, the experiment, the novel aspect of the experiments with regard to the stratified medium was the observation of edgewise settling. The broadside on settling, that was the first phase, is already known for a homogeneous ambient, and it is due to inertia. So inertia is not the most important player here. Okay, what we need is the influence of stratification. Okay, so as far as the anisotropic particles are concerned, we're going to model it as a spheroid. Okay, so I'm not going to go into any details, but you can do the analysis for the entire range of aspect ratios. So the particle geometry is characterized by kappa, the particle aspect ratio, and I can go from a very thin disk, which corresponds to an aspect ratio of nearly 0, a very thin oblate spheroid, okay, which is the sort of particles, remember, were used in the experiments, down to very large aspect ratios, which corresponds to needles or very slender fibers. Okay? So we are going to discuss the orientation dynamics as a function of this aspect ratio. Okay, so I just want to comment on the method used. Okay, and the method used is known as the reciprocal theorem. And since many of you may not be familiar with this method, I'm just going to introduce briefly an example of how the calculation proceeds. The actual calculation is too detailed and complicated to show. So there are references that appeared in the initial slide. People can look it up. Okay. So the reciprocal theorem in its original form is known as the Lorentz reciprocal theorem. And what it does is it relates a pair of stress and velocity fields. So sigma 1 and V1 are the stress and velocity field of problem 1, let's say, and sigma 2 and V2 are the corresponding fields of problem 2. And the reciprocal theorem relates them in this fashion. So there is a cross coupling between the velocity of one problem and the stress field of another, and which form the integrants of two surface integrals. Okay. And the Lorentz reciprocal theorem was valid in the Stokes approximation, but you can easily generalize it. In the Stokes approximation, the stress field is the usual viscous stress. It's minus pressure times the identity plus 2 mu times the rate of strain tensor. So the Stokes approximation essentially amounts to saying that the divergence of the stress field is 0. Okay? Now you can therefore allow for a non-zero divergence of the stress field. So if it's inertia, we know that the divergence of the stress field equals the acceleration. Okay? And this becomes the generalized reciprocal theorem. Okay? And the way in which you use the reciprocal theorem is that sigma 1 V1 is usually the problem of interest, the problem that you want to solve, the answer for which is not known. And you try to leverage your knowledge of a known test problem, sigma 2 V2, which is a simpler problem, and therefore the answer to it is no. Okay, so without going through the idea of the reciprocal theorem is that if you have a perturbation expansion, you don't need to actually calculate the terms in the perturbation expansion at the relevant order. There are shortcuts and shorter ways of doing this in terms of the leading order solution itself to try and calculate the quantity of interest. So I'm just going to illustrate this for a simple case, and that's to determine the inertial correction to the Stokes drag on a spherical particle. I'm saying this because we saw the inertial screening length, okay, and this inertial correction was first determined by Owing. Okay, so the Stokes drag on a spherical particle, as most of you know, would be 6 pi mu UA. And the objective here is to calculate the correction when the Reynolds number is no longer 0. So the first correction that is proportional to the Reynolds number. It turns out to be order RE in this case. Okay, but though it is order RE, it's deceptively simple. It's a singular perturbation problem. And in fact, it's sometimes this problem is referred to as the Whitehead's paradox, because a regular perturbation that was originally done by Whitehead, this is detailed in the textbook by Gary Leal, for instance, doesn't give you an answer. It fails to satisfy boundary conditions. And it was Owing who realized that you need to account for the inertial terms at leading order to get this correction. Okay. So the idea is, let's pretend that this problem of determining the inertial correction is really what we want to solve. Okay, so that's the governing equation. So I have actually replaced this velocity in the inertial term by the ambient flow, but you can think of it as small u1. So this is the inertial acceleration. And then you have the continuity. Okay, that's the no slip boundary condition on the surface of the sphere. That's the far field decay boundary condition. And then the test problem, sigma to u2, remember, is a simpler problem. Okay, so that's just the Stokes equations. So you have Stokesian translation. Now, if you just specialize that reciprocal theorem identity here to this case, then you get the following. So the only difference between the earlier identity and this one is that del dot sigma 2 is not there. And that's because del dot sigma 2 is 0. You've chosen a test problem that's a Stokes problem. Okay? And so you have two surface integrals. And the key is now to use your knowledge of the test problem to write those surface integrals in closed form. So if I look at this integral, the first integral on the right-hand side, I know u2, small u2 is exactly capital U2, the translational velocity of the particle in the test problem, which is a constant. So I can pull it out, which I've done here. As soon as I've pulled it out, the reciprocal theorem, the surface integral, gives me the quantity of interest. Integral sigma 1 dot n ds is precisely the force that I'm looking for. Okay, so that's the quantity that is to be determined in terms of the other two terms. Okay, the other surface integral is known in closed form because u1 again is a constant. I can pull it out. Sigma 2 dot n is the surface force density of the Stokes problem, which in fact is known. It's 3 halves u2 that you know, provided you solve the corresponding Stokes problem. So this immediately on the left-hand side, in fact, gives you 6 pi u1 dot u2. Okay, this here involves the f1 dot u2, where f1 is the force, unknown force in problem 1. And then you have a residual volume integral that involves the inertial acceleration. So in effect, what you're doing is you're adding up the inertial acceleration force field at every point in the domain, summing it up over the unbounded domain, mediated by a kernel, that is the velocity field in problem 2, and that gives you effectively the inertial correction. So again, u2, the velocity field that appears in this integral, is again known. That's the Stokes field. Okay, and therefore you know the Stokes solution. I've written this down in closed form, so you don't need it in its full form here. Okay, so if I use that, the fact that the u2, the full velocity field, is linear in the boundary velocity, the velocity of translation of the sphere. Okay, that's because of the linearity of the Stokes problem. Then I land up with the reciprocal theorem where all of the terms are multiplied by u2. u2 is arbitrary, so I can just pull it out. Whatever multiplies it must be 0. And I get an identity, a formal identity for the force on the sphere. And you can see that it is 6 pi u1 in non-dimensional terms, plus a correction proportional to Reynolds, where I know k2, and there are ways of calculating this inertial acceleration. So if I can evaluate this volume integral, I would have calculated what Oseen first determined. Okay, and this correction is in fact turns out to be 3 by 8 times 6 pi. In fact, this integral is again deceptively simple. The contribution to this integral in fact comes from largest the scales of order, the inertial screening length. So the analysis is better done in Fourier space using a convolution theorem. But if you do recognize that, then you can really complete this calculation in half a page. Okay, so that I'm just saying that to tell you the value of the reciprocal theorem. So what was originally a very long calculation, and you can see this in Leal's textbook, for instance, can be made very short using the reciprocal theorem. If you know that if you can very judiciously choose your test problem and the actual problem in terms of what is the definition of the velocity and stress fields. Okay, and then finally recognize where the dominant contribution to that integral comes from. Okay. So this is the reciprocal theorem answer for the actual problem. Okay, remember, we are considering spheroids. And I just want to tell you that in the example problem, we asked for the force. And the test problem, remember, was Stokesian translation of a sphere. In the actual problem, I'm asking for the rotation of a spheroid. So you could think of it as I'm asking for the torque acting on a spheroid. And it turns out that the appropriate test problem is the Stokesian rotation of a spheroid. Okay, so the second order tensor K2 here is just replaced by a more complicated entity U2. Okay, and so this is the formal expression here, and you can immediately see that the dimensionless parameters that we have already introduced. There's the Reynolds number, and there is the viscous Richardson number. Okay, and so intuitively, the first term that is proportional to the Reynolds number is the inertial torque. Okay, and when we are talking about a weakly stratified ambient, weak in the sense that the viscous Richardson number is very small, you can evaluate this inertial torque at leading order is just equal to what it is for a homogeneous ambient. And we had calculated this for a spheroid a few years back as a function of its aspect ratio. I'm not showing the detailed expressions, but you can do it in closed form because the velocity field can be written down in terms of spheroidal harmonics. Now, this is the new part, the part proportional to the viscous Richardson number. And you can see it has two contributions. Okay? One, a hydrostatic contribution, and the second one, a hydrodynamic contribution that relies essentially on the density perturbation, rho prime, which we used in our preliminary scaling arguments. Okay, that is generated by the flow field itself due to convection of and diffusion of the density perturbation. Okay? So let's start with the simplest case. The simplest case is the hydrostatic torque. This torque is there even if the fluid is static. Okay, and the spheroid is sitting in a stratified medium. You can think of it in terms of the equivalent, in terms of the Archimedean interpretation. I replace the spheroid by an equivalent spheroidal fluid blob, except that the fluid blob is stratified, and therefore the center of mass of the fluid blob lies below the geometric center of the homogeneous spheroid. The buoyancy force has a lower point of action for both spheroids. Therefore, there is a couple, and you can easily argue that that couple will turn the spheroid broadside on. Okay, not edgewise as observed in the experiments, but broadside on. This is quite straightforward to calculate. Next is the inertial torque, and remember, we can approximate it based on the homogeneous ambient. Okay, and this again supports a broadside on equilibrium. Okay, now intuitively you can argue is that this is because of wake shielding in the sense that when I have an inclined prolate spheroid as I've shown here, then the rear part of the spheroid is quote unquote shielded by the wake that emanates from the front part. And that shielding causes the rear part of the spheroid to catch up with the front, implying that the spheroid will adopt a broadside on equilibrium. Okay? Now, notice that this is strictly not true because at small Reynolds, the wake exists only at distances of order the inertial screening length. But the qualitative argument is the same because the inner field mimics the symmetry of the wake field. Okay? And then comes the main part, the hydrodynamic stratification torque. So importantly, remember both the inertial torque and the hydrostatic torque rotate the spheroid broadside on. So the only way we can explain the experiments is if the hydrodynamic stratification torque were to do the opposite. And here it relies on the distribution of the density perturbation, and therefore we have to make an assumption about the Peclet number. Okay. Now it's convenient. The arbitrary Peclet would have to be numerical. So we assume Peclet to either be small or large, that is the diffusion dominant limit or the convection dominant limit. And let me remind you again that large Peclet corresponds to the experimental scenario, closer to the experimental scenario. Okay. But I'll nevertheless go through the small Peclet case. Okay. So when I have the diffusion dominant limit, okay, I just sketch the equations here. The density just satisfies the diffusion, homogeneous diffusion equation, the Laplacian here. And the density has to satisfy a far field decay condition. And the flux has to be zero because the particle is impermeable. And therefore here it just says that the flux based on the perturbation density gradient has to be negative of that for the ambient density gradient. Okay? And you can see what the particle does to the isopycnals. So this is just a qualitative sketch of the isopycnals. In the absence of the particle, all the isopycnals were horizontal, okay, because of the stable stratification. But when you have the particle in there, the particle is impermeable. So the isopycnals have to bend so as to meet the particle surface at right angles. And that's what I've sketched here for the oblate and prolate spheroid. Okay, you can see they're rather slender. It turns out for the oblate spheroid, even as it gets infinitely thin, there is a finite effect as far as the density perturbation is concerned. But the effect rapidly decays for a prolate spheroid. Okay. Now, given this density field, the idea is just that the bent isopycnals will generate a baroclinic flow, okay, and that flow will rotate the spheroidal particle. So I'm just Many of you would already be familiar with this, but for those of you who aren't, I'm just illustrating it for a very simple case where imagine that you have tilted a vessel, okay, impulsively, so that instantaneously the fluid level in the vessel is not horizontal, okay, and it's at this inclination. Okay, now we intuitively expect that there's going to be a sloshing mode setup, a standing gravity wave, and over long times it will return to the horizontal. But and the gravity wave is associated with the potential flow in the bulk. Okay, but you can also think of this potential flow being induced in terms of a baroclinic vorticity distribution. The difference is that here the liquid has a constant density, so the baroclinic induction takes place entirely at the interface, and that's because the gradient of density here is localized at the interface, pointing towards the higher density fluid. Okay, if we imagine the fluid as instantaneously stationary, the pressure gradient is along gravity, and therefore you have the constant pressure and the constant density contours not being coincident. And from the vorticity equation, you have a generation term, and that generation tells you that there will be a vortex sheet at the surface that will then induce the restoring flow. Okay, so exactly the same thing happens for a sphere. Okay, and you can see that the flow field in this case has a dipolar character, an extensional character. Okay. Of course, for a sphere, there is no rotation because of the symmetry. For a spheroid, the flow field has an identical character, except that it's no longer symmetric. It looks like this. Okay, and that asymmetry means that the spheroid will rotate. So in other words, there will be a hydrodynamic stratification torque. Now, it's not straightforward as to how to predict the direction. You will see that in a moment. Okay, but what you can predict is that, remember, the torque comes from the modulation of the density field in a region around the spheroid. This is what I meant when I said early on that for small Peclet, it's a regular perturbation problem. The contribution to the torque arises from length scales of order the spheroid size. In this case, it's major axis. Okay, and therefore, the scale for the hydrodynamic stratification torque is a regular scale. It's just proportional to RIV. Okay, so therefore you have three torque contributions: the inertial torque contribution of order Reynolds, and the hydrostatic and hydrodynamic stratification torque for small Peclet, both of which are order Richardson number, the viscous Richardson number. Okay, now an important aspect here for small Peclet is that all the torque coefficients have the same functional form. And what do I mean by this? Okay, I mean, if you look at the sketch here, I've denoted a prolate spheroid with the gravity pointing vertically downward, and there being an angle C between the orientation of the spheroid and G. So it turns out that all of the three torques have the same dependence on that angle C. And that dependence is just sine C times cos C. And that's because of the regular perturbation nature of the problem. Because of the regular perturbation, you can in fact infer that dependence using a simple scaling argument. The torque must be quadratic in G. Okay, that has, for instance, that has to do with, in the inertia case, that has to do with the acceleration being quadratic in U, and U being the Stokesian field, which is linear in G. Okay, so you basically had to construct a pseudo vector, which is the torque, that is quadratic in G and in terms of P. And it turns out that this is the only way you can do it. So L has to be proportional to G cross P times G dot P. G cross P is sine C, G dot P is cos C. And therefore, what is the detailed solution really determines is just this torque coefficient, which is a function of the aspect ratio. Okay, so you can characterize this problem entirely in terms of a torque coefficient calculated as a function of the spheroid aspect ratio. The spheroid torque will just look like this. Okay, so it's maximum at pi by 4 at an orientation midway between the broadside on and long side on orientations. Okay, going to 0 at those particular limiting orientations. Now you can do this for each of the three contributions. That's the hydrostatic torque there. That's the inertial torque. And that's the hydrodynamic torque. And what I want you to just note is that the solid lines are for the prolate spheroid, the dashed line for the oblate. And you can see that the solid line and the dashed lines have interchanged positions for the hydrodynamic case. Okay, that immediately implies that in contrast to the hydrostatic and inertial cases on the left, the hydrodynamic torque in fact rotates the particle edgewise. Okay, at least So for the prolate particle, for the prolate spheroid, it is edgewise regardless of the aspect ratio. So the horizontal axis is the spheroid eccentricity, and I go from a sphere to a very slender needle-like shape. And this is being plotted, the torque coefficient, as a function of the eccentricity. Okay. Now, it turns out, unfortunately, that at small Peclet, the magnitude of this curve, the black curve, is actually less than that of the hydrostatic coefficient. And therefore, even though the hydrodynamic torque does the right thing in terms of consistency with the experiments for a prolate spheroid, okay, the hydrostatic broadside on contribution dominates, and therefore these spheroids at small Peclet will always turn broadside on. The total torque supports a broadside on equilibrium. Okay? So interestingly, the oblate spheroid torque actually changes sign across a critical aspect ratio. Okay? So that's the small Peclet case. Okay? So now I want to go to the convection dominant limit. Okay? And what I'll do is, so this is the volume integral that again, the focus is only on the hydrodynamic stratification torque because that's the only component that cares about Peclet. Okay? So now I'll estimate what is the integrand. Okay, so the integrand is to be, the integration is over the unbounded fluid domain outside the spheroid. Okay, so I want to estimate how do these disturbance fields behave as a function of distance from the spheroid. Okay? Now rho prime, if you notice, rho prime was what I originally estimated in terms of when I calculated the large Peclet stratification screening depth. And at the time I pointed out that rho prime is independent of R. Okay? So in dimensionless terms, rho prime is just order 1, and that just comes from the convection of the base state stratification by the order 1 by R Stokesian field over a distance of order R. So rho prime is order 1. U2 is the disturbance velocity due to a rotating spheroid. Okay, now a translating particle generates a 1 by R field in Stokes flow. A rotating particle is like a forced dipole. Okay, and therefore the velocity is 1 order smaller. It's 1 by R squared. G is just the unit vector along gravity, and therefore the integrand, which is the product of U prime and U2, decays like 1 by R squared, whereas the volume dV grows like R cubed. Okay? And it turns out, therefore, that if you use Stokesian estimates, the integral diverges like R. Okay? That's an indication that the contribution is not coming from length scales of order the spheroid. It's coming from much larger distances. And for large Peclet, we know that this large distance is the stratification screening length that we originally spoke about, that scales as the inverse cube root of the viscous Richardson number. So if you say that the stratification torque integral diverges like R, but that divergence is cut off at the stratification screening length, which is RIV to the minus 1/3, you multiply that RIV to the minus 1/3, the finite but large estimate of the torque integral times RIV, and you get the fact that the hydrodynamic torque is now RIV to the 2/3, unlike small Peclet, where it was just order RIV. And therefore, regardless of aspect ratio, for sufficiently small RIV, this hydrodynamic torque is going to be the most dominant. It's going to be dominant over the hydrostatic torque. Okay. So the competition now, as far as orientation dynamics is concerned, is just between the hydrodynamic stratification torque and the inertial torque that we already know. Okay. So this is to just tell you that the calculation is involved. Okay. I've not shown you the details. I'm going to directly show you the results. Okay. And the result is, I've just drawn the torque curves now. So remember, for small Peclet, I'd shown you the torque coefficient as a function of the spheroid aspect ratio. And that's because we already knew the torque dependence was the product of a sine and a cosine based on scaling arguments. But those scaling arguments only work for a regular perturbation. Okay, and therefore, for a singular perturbation, you can see that this torque curve is no longer symmetric about pi/4 for either the prolate or oblate. That's a betrayal of the fact that the origin is singular. Okay, and the angular dependence is therefore not simple. So you have to plot it as a function of angle for the different aspect ratios, which is what I've done. Okay, so for very nearly spherical particles, that's this red curve on top. If you scale it appropriately, you will see that that's actually, though it's very shallow, the peak is at pi/4. Okay, so for nearly spherical particles, still behave like the small Peclet problem. But as you increase the aspect ratio, the torque takes on a different shape, with the peak approaching a certain limiting angle that is larger than pi/4 for a prolate spheroid, but smaller than it for an oblate spheroid. Okay? Now, this is very important. Just to highlight this, what I've done here in these plots is divided it by the symmetric dependence that we know occurs for the inertial torque. Just to show you that as I increase the aspect ratio, the stratification, so if the dependence were to be sine times cosine, that would just appear like a horizontal line on this plot. Okay? And the distorted dependence is indicated by these curves, which tells you that the stratification torque is greater than the regular angular dependence when C is greater than pi/4 and less than it when C is less than pi/4. Okay? And the opposite holds true for the oblate spheroid. Now you have both the components of the torque. Okay, you have the inertial torque, which remember was symmetric with a peak at pi/4. And I've done this for a prolate spheroid, these sketches. So we know that the stratification torque is biased towards larger C, closer to pi/2. Okay. Now what you can do, you can imagine is that you can imagine an experiment where you're increasing RIV. We'll see how that happens, the viscous Richardson number. So in other words, you're making the stratification stronger, and therefore the dashed curve will keep increasing in amplitude. Okay. And you can see that because the angular dependence is not the same, as it increases in amplitude, there comes an intermediate range of amplitudes where the two curves intersect at a single point, giving rise to an equilibrium orientation that lies between the horizontal and vertical orientations. Okay. And you can show that this orientation is in fact stable. So if you perturb the spheroid on the left, the stratification torque rotates it back to C equilibrium, and on the other side, inertial torque does the same. Okay? And then finally, beyond a second critical amplitude, okay, the stratification torque becomes so large that there are no points of intersection any longer. The stratification torque is completely dominant, and it's again edgewise. Okay, so both the small Peclet and large Peclet torques are edgewise, except that for large Peclet, the stratification torque is dominant over the hydrostatic one because it scales like RIV to the 2/3, and therefore the particles will orient edgewise. Okay, so I have this behavior where with increasing RIV, I first have a horizontal broadside on settling, okay, where inertia is dominant. And then I cross a threshold where I see an intermediate inclined orientation. And then these inclinations smoothly move towards the vertical or edgewise orientation. And beyond a threshold, second threshold, I have the edgewise orientation. Okay, so I can organize my results like so. I have two critical curves here, a lower threshold and an upper threshold. Okay. I have this critical dimensionless parameter ratio. Okay, so remember, the stratification torque was RIV to the 2/3, and the inertial torque was RE. Okay, so therefore the ratio of the order of magnitudes is really proportional to RIV by Reynolds to the 3/2. So this is the critical ratio of dimensionless parameters that should govern the orientation dynamics in the limit of weak inertia and stratification. And I plot that as a function of spheroid aspect ratio. Okay. In the limit of a sphere, the torque dependencies are simple. They're proportional to the product of the sine and cosine. And therefore, I don't have two thresholds. The thresholds coincide into a single threshold. I have a direct transition from broadside on to longside on equilibria. But as I elongate the sphere into a prolate spheroid, I have a gap that emerges that allows for inclined orientations. Okay? And exactly the same happens for an oblate spheroid. Okay, the only difference is that these curves approach finite plateaus even for a flat disk, whereas for a prolate spheroid, you can show that this is really a logarithmic decay. Okay. So now, having done this, as the last part, I just want to go back to the experiments to try and interpret them. Okay, so we know enough to do that. And so this is the experiments that I spoke about initially, the ones by Mercier. Okay. And so remember that in theory, RE and RIV are fixed dimensionless parameters. And so we want the buoyancy frequency to be fixed, okay, and the settling velocity to be fixed. Okay, but in practice, that's not the case. As you can see in the experiments, the vertical dashed line is certainly more or less fixed, notwithstanding small changes. So the buoyancy frequency is fixed, But if you remember, I told you that there was a certain level here, which is 0 here, at which the particle density becomes equal to the fluid density. The density is increased enough here to equal the particle density. And therefore, for sufficiently long times, the particle isn't going to translate. It's going to come to rest at this neutral buoyancy level. Okay. Therefore, what happens with time in the experiments is that the velocity decreases. The settling velocity will gradually decrease as it approaches the neutral buoyancy level. And we are at in the weak inertia stratification limit, we can think of it as an overdamped approach. So there are not going to be any oscillations. So in effect, what we are saying is that because of this change in the settling velocity, we can think of the theory in terms of a series of quasi-static equilibria, okay, where the Reynolds decreases and the viscous Richardson number increases as a function of time. So in other words, at each time instant, the momentum around the spheroid diffuses fast enough to set up a quasi-steady field, and I get a torque that conforms to the theoretical approximation still, because I regard this whole approach to the neutral buoyancy level as a very slow one. Okay? And therefore, I can think of the approach as being an increase in this ratio, because the viscous Richardson increases, the Reynolds decreases, so this ratio is increasing. Okay? And therefore, I go along this upward arrow. So the idea is that to begin with, when I'm right at the top, the particle, the density difference driving the sedimentation is large. Okay. And so this ratio RIV by RE power 3 by 2 is below the lower threshold. And I have a behavior similar to the homogeneous ambient. I have settling in a broadside on equilibrium. Okay. And then at some point, as the particle slows down, specifically at that point, I have arrived at the upper threshold, and the horizontal orientation has now become unstable. And so I will proceed through a sequence of intermediate orientation equilibria as I span this gap. Okay. And then finally, I arrive at the vertical threshold, and I will be vertical above that green curve. Okay. Except that finally, I'm so close to the neutral buoyancy level that U has become negligibly small. Okay. And the hydrostatic contribution has become dominant, and the hydrostatic contribution turns the particle back broadside on. Okay, so qualitatively speaking, the sequence of events mirrored based on this orientation dynamics is very similar to that observed in the experiments. Okay, and you can repeat the identical argument for a prolate spheroid. This is for an oblate spheroid because the experiments was for disks. So in terms of the second experiment, the most important thing was there wasn't a neutral buoyancy level. So in other words, the particle was so dense, you can think of the neutral buoyancy level as being far, far below the tank. Okay. And therefore, the velocity isn't slowing down that much. It's almost constant. And therefore, it's reasonable to think that the intermediate equilibria will be maintained because of the near time independence of the settling velocity. And what they observe for the thick disks seems to mirror that. So you can see that for the thick disks, which you can show correspond to the region between these two curves, okay, and therefore to the region of intermediate equilibria, the experimental signature is consistent. They seem to preserve this orientation until they move out of the stratification zone into the homogeneous zone. Okay. So this is what I wanted to end with. So you can successfully implement the experiments, interpret the experiments based on what we have found. Thierry, do I have a little time more, or?
It's almost over. So
okay.
You know what you mean by little time. If you can conclude.
Give you a slide with some future directions. We have just
okay. Let's see to this slide. Thank you.
Yeah. Okay. I'll be happy to answer any questions. So one of the things that we want to do is to consider inertia, so that we want to organize the orientation dynamics in a three-dimensional parameter space.
If you want to present them, but in 1 minute, if you want.
Okay. So, well, I just want to do one thing. So I want to return to the sphere case. So just to return to the original argument, remember we said that for the biogenic mixing, we are talking about a modification of the velocity field at large distances. So this is how the flow field looks around a sphere for large speckling. Okay, and interestingly, even in the absence of inertia, there exists a reverse jet behind that sphere. And even more remarkably, the velocity in that reverse jet decays like 1 by z. So it's like a Stokes, if you move along the rare stagnation streamline, there is a Stokeslet followed by a reverse Stokeslet decay at still larger downstream distances. Okay. And this is something that we have calculated just very recently, in that the structure there is really complicated. It's very intricate and very sensitively dependent on diffusion. So be happy to discuss this with anyone interested at a later time. I'll be happy to answer questions.
Okay, thank you, Ganesh, for this talk and very interesting comparison with experiments performed by somebody that we know quite well, Mathieu Mercier. Do you have any questions among the participants? Not really. Okay, so thank you very much, Ganesh. Maybe we can